Alright, some solved problems for chapter 40. So I have an electron that is a free particle moving in the negative x direction. That means my momentum is going to be negative, and it's giving me my momentum, and I'm just looking to write the wave function for this guy. Since it's a free particle, I can write it as such. Now I need to figure out essentially k and omega. So how do we go about doing that? Well, E is going to be equal to h times f. We can always say that, which is going to be equal to h bar multiplied by omega. Omega is 2 pi times f. And we can also say the momentum is going to be equal to h over lambda. But we can also write lambda as 2 pi over k. So we could write this guy as h bar multiplied by k. I just want to have those guys written down. So we can essentially say that this constant k is going to be equal to p, the momentum, divided by h bar. And so this is going to be 4.5 times 10 to the negative 24th divided by 6.626 times 10 to the minus 34th divided by 2 pi. Now we can't forget that this guy is going in the negative x direction, so that's going to be that negative sign just right there. And so that tells me that my k is going to be equal to negative 4.27 times 10 to the 10th with the unit of inverse meters. Now we can also kind of say, well, we do know that the energy is going to be equal to the momentum squared divided by 2 times the mass. And since we can say that the energy is going to be equal to h bar times omega, so we could say h bar times omega. Now I should be able to figure out what omega ought to be, and just with a little bit of rearranging you convince yourself that omega is going to be equal to h bar multiplied by k squared divided by 2 times, in this case, the mass of the electron. So it's going to be the same thing, 6.626 times 10 to the minus 34th divided by 2 pi multiplied by k squared, where I'm going to just use the same k just like that. Call me lazy. Oop, don't forget to square that guy. And then 2 times the mass, in this case of an electron, 9.11 times 10 to the minus 31. And you go ahead and you type all that in, and we're going to get 1.05 times 10 to the 17th inverse seconds. And essentially all we're going to do is we're going to be plugging that guy in just right up there. And then we're going to be plugging this guy in just right there, and we should be good to go. One thing to kind of keep in mind is we do want to have the normalization criteria, where if we integrate this, psi star psi dx from -1 to 1, that is going to be equal to 1, and that should convince you that this constant a must also be equal to 1. And so there we have it. Just plug those guys in, and we're good to go. Okay, so problem number 5. Now I have some wave function that looks like a sine, and I know the value for that constant, and I'm looking for when we have, for what value of x are we having the highest probability of finding a particle described by that wave function. So essentially I'm looking for psi squared is equal to 1, or at least equal to a maximum. And so this guy is going to be equal to a squared multiplied by sine squared of kx. And this guy is going to be a maximum, essentially, where kx is equal to 1. Now where is that going to occur? Well, since k is 2 pi over lambda, I'm essentially going to say kx is going to become 2 pi x multiplied by lambda. That's going to be when it's equal to n pi divided by 2, where I would say n is going to be equal to 1, 3, 5, all the odd integers. And so we would say that this thing is going to have a maximum when x is equal to n lambda divided by 4, again, where n is equal to 1, 3, 5, and so on and so forth. So that's part A. For part B, I'm looking for where essentially psi squared is equal to 0. We're going to have the lowest probability, and not surprisingly, that's going to be where sine squared of kx is equal to 0. And that's going to happen when I have my kx, 2 pi x over lambda is going to be integer multiples of pi, so n in this case is going to be equal to 0, 1, 2, and so on and so forth. And so essentially I'm going to say that this is going to be x is equal to n lambda divided by 2, where n is equal to 0, 1, 2, and so on and so forth. So there's my answers for A and for B. And now let's work some particles in boxes. We talked about electrons, we can always talk about protons, and we're going to have some energy given to us in MeV for this proton. It has a width of L, and we need to convert this guy to joules, so this is going to be 8 times 10 to the negative 13th joules. Should be good at doing those conversions right now. And what we're going to do is what must the box be for that to be the ground level energy, and so this is going to be E1. So we're just going to rearrange the equation we have for a particle in a box and solve for L for the ground level energy. So this is going to be 8 times the mass times the very first energy, and so pretty straightforward, 6.626 times 10 to the negative 34th divided by 8. Be careful here, this is the mass of a proton, so 1.6 times 10 to the negative 27th. And then we're going to have the energy, so 8 times 10 to the minus 13th. And I did forget my little square sign on this side, so go ahead and put that guy in. And this box is going to be about 6.4 times 10 to the minus 15th meters, which is actually about the size of a nucleus, and so that's kind of a good thing. Okay, a little bit of practice with some tunneling. If we have an electron and it's got some initial kinetic energy of 5 electron volts, comes across a barrier with first 7 eV height to it and a certain width, what's the transmission coefficient? Now keep in mind that you either need to work in electron volts or in joules, and I'll just go ahead and work in joules for this one. So because these are ratios, I can work them in electron volts when it comes to figuring out what G is, however. So that's going to be 16 times 5 divided by 7, 1 minus 5 divided by 7. Just be careful how you type that into your calculator, and you're going to get 3.265, at least for part A. For this little kappa right over there, that's going to be the square root 2 times the mass of an electron, 9.11 times 10 to the minus 31st. And then we're going to have our energy difference, which is going to be 2 eV. It's going to be 5 minus 7. And I'm going to go ahead and convert this guy to joules, multiply it by 1.6 times 10 to the negative 19th. And go ahead and divide this guy by h bar, 6.626 times 10 to the minus 34th divided by 2 pi. Actually, that's an explicit divided by. And we're going to get a really big number. It's going to be equal to 7.24 times 10 to the 9th. And actually, it's going to have a unit of inverse meters to make all that guy work out. And so we're going to get a transmission probability that's going to be equal to 3.265 multiplied by e to the negative 2 times kappa, 7.24 times 10 to the 9th, multiplied by the barrier width, and that's going to be 0.6 times 10 to the negative 9th. You go ahead and you type all that in, and we're going to get a relatively small probability, 5.5 times 10 to the minus 4th, and that's the answer for part A. For part B, as we increase the potential that it is incident upon, we would expect the probability to go down, and I'll spare you typing all that in. For part B, we're going to get a 1.8 times 10 to the minus 5th, and for part C, we're going to get 1.1 times 10 to the minus 7th. So again, as we increase the height of the barrier, the transmission probability goes down. Let's just take a quick look at what this looks like graphically in a fun little PhET simulation here. So here I have my wave packet, and here I have a barrier that I can actually mess around with. And this is going to be the probability of finding this wave packet. And as this thing is incident upon it, taking a look at the probability down here, I'm going to go ahead and pause that. What we kind of saw is that there was a sinusoidal looking function over here, and we actually saw that energy was not created or destroyed, and so when it hit this barrier, it had to go somewhere, and so actually it bounced backwards. what we were kind of measuring is the transmission probability. You can see it's relatively low, and as time goes on, we're talking about femtoseconds here, the probability gets smaller and smaller and smaller and smaller. We can go ahead and make this thing just a little bit smaller, and we should see some higher probabilities of this thing going through it, which is more or less what you'd expect. And again, as we made the barrier higher, it would be harder to penetrate. And lastly, let's finish off with some harmonic oscillators. Here we have a wooden block on the end of a spring that has some force constant, and let's calculate the quantum ground level energies. And so at ground level, in this case, is going to tell me n is equal to 0, and we're going to say E naught is going to be equal to just 1/2 h bar omega, where omega is going to be equal to the square root of k prime divided by the mass. And so this guy right over here is going to be equal to 110 divided by 0.25 kilograms. And so that's going to give me 21 radians per second. And so the ground level energy is going to be equal to 1/2 multiplied by 6.626 times 10 to the minus 34th divided by 2 pi multiplied by 21. And we're going to get this guy being equal to 1.1 times 10 to the minus 33 joules, which is going to be equal to 6.93 times 10 to the minus 15 electron volts, which is really, really, really small. So are quantum effects important for this harmonic oscillator? No, they are not important. Let's go ahead and calculate delta E. So that's going to be equal to E of n plus 1 minus E sub n. You can kind of convince yourself that this guy is going to be equal to h bar multiplied by omega. And this is actually just going to be 2 times my original energy, this guy right over there. And so we're going to be talking about energies that are 2.22 times 10 to the minus 33 joules, or 1.39 times 10 to the minus 14 electron volts. So really, really, really small energy separations. Quantum effects are not important for your standard oscillating masses on springs.